Hey guys, topic 10 review. Let's do it. The essential question says, when lines intersect a circle, how are the figures formed related to the radius, circumference, and area? So, when lines, okay, or plural lines intersect a circle, how is it related to the radius, the circumference, and the area? Okay, so we notice if this line goes here, then to find the area of that, we have to draw in radiuses and figure out the area of the sector and then subtract the area of that triangle. Do you see the kind of how that plays together there? So to find the area of that green object called a sector, it interacts with the whole area of the circle. It's a portion of the circle. We notice too that if we wanted to, let's just step that back. If we wanted to calculate, let's say, an arc length of this or an arc length of that, that's interacting with our radiuses as well. We had to use a radius to prove how that dimension, how this angle and this angle would be formed, right? So these objects, I guess we could call them objects, all these objects are influenced by the radius, the circumference, and the area of our circle. We use those three measurements to calculate other figures. I guess I'm using the word objects in the same way I'm using figures. So looking at our vocab word that says a blank is a region of a circle with two radii. So a blank is a region of a circle with two radii. So let's just add two radii. And it says it's a region and an arc. So two radii and an arc of a circle as borders. And so when they use the word region, it sounds like they're talking about the whole area. That is what we would call the sector. Okay, so that's our sector of a circle. A blank is an angle with its vertex on the circle. Okay, so I could use the same circle here. If the angle's out here on the vertex, we know that that angle is inscribed. It's an inscribed angle. A blank and the corresponding circle have exactly one point in common. Okay, that was our central angle chord, intersect, secant, segment, tangent to a circle. That sounds like a tangent. So let's put the word tangent in there and see if that makes sense. A tangent line and its corresponding circle have exactly one point in common. Yeah, we like that. That's our tangent. And so, yeah, so we've used each of these. Now it says, when both rays of an angle intersect a circle, the blank is the portion of the circle between the rays. So using this same thing, same circle, right? If I have an angle, so let's say our angle's out here. If both of the rays, so this ray and this ray, intersect the circle, then blank is the portion of the circle between the rays. So this is what we call the intercepted arc. We also, when we used inscribed angles, we talked about this being our intercepted arc. So I like this word, intercepted arc. Nice. Now, lesson 1-0, this is our blue and green foldable. So it's saying it's a portion or a fraction. So this first example, they already worked it for us. They said, what if circle J has a radius of 6? What's the area if it has a central angle of 80. So we said the area of our sector is 80 over 360 times the portion of the area we want. So the area is pi r squared, so that's pi times 6 times 6. Notice this is how they built the equation, and they found the area, it's 20.1. And this decimal kept going. Obviously, this was a big long decimal, and they just decided to round to the nearest tenth. Now here we get some practice, not exactly like our foldables. And I warned you about this, and we did this in some of our homeworks. We're going to leave our answer in terms of pi. So if I think about this here in this last one, what all this stuff did I have in the pi? I had this 80 divided by 360 times the 6 times the 6 times pi. What they're saying is don't multiply by pi, just multiply by this stuff. So this last one would have been 80 divided by 360 equals times 6 times 6. Okay, so this would have been 8 pi. To double check my answer, if I take 8 times 3.14, I get 25.12. So see how that is the same. 8 pi is the same as 25.1. All right. However, 8 pi is actually more exact of an answer. And so that's why that's usually the preferred method. So let's practice that. Our arc, JK, is not the whole circumference, it's a portion. So this angle would be this angle. And so our arc length S would be 112 over 360 times the circumference. So that's 2 times pi times the radius, 5. Now they want it in terms of pi. So we want in our calculator, we want to take these numbers and then hold off on multiplying by pi. So I'm going to do 112 divided by 360. Enter, times 2, enter, times 5, enter. I get 3.1 repeating pi. I'll do that again. 112 divided by 360, enter, times 2 times 5. Yeah. All right, what about arc AB? So do you see how this is less than 180? This would be called a minor arc. So what's going on here? Well, they're using 3 letters, but let's see where this goes. So A, B, C. Notice how it's greater than 180, so that's called a major arc. So just like I use a obtuse angle and an acute angle, I use major and minor to talk about arc lengths that are greater than 180 or less than 180. So this angle does actually not correspond with the arc we want, but we know that all the way around is 360. So we'll take 360, take away 154, and we get 206. So my central angle 206 is the arc length I'm looking for. I'm looking for the arc length that goes with the angle, central angle 206. And then it's 2 times pi times the radius, 8. Okay? So typing this in my calculator, holding off on multiplying by pi, 206 divided by 360 equals times 2 times 8. Okay, I get 11.5 repeating pi. Now to find the area in terms of pi. So once again, just like our foldables, we're just going to not multiply by pi. Leave that last step undone. And they're asking for the sector, which is the area of this piece. They want the sector in RM. Here they want the sector DSE. All right. So if this is 63, this is our central angle. So the area of my sector is this portion of the circle times the radius, pi radius squared, pi times 10 times 10. Now we're going to multiply just these numbers to find the area of our sector. All right, I get 17.5 pi. Here, the area of my sector would be 172. and pi radius squared. So pi times 7 times 7. So 172 divided by 360 times 7 times 7. 23.41 repeating pi. Last question in the section. If you know the circumference of a circle and the area of the sector, so this was off of our foldable. It's this portion or arc length times my circumference, or our sector is this portion times the, got this wrong. This would be S, and this was the area of a sector. If I know my area of the whole thing, how could you determine the central angle? So we did this twice on our foldable. We would do this Lynch swap. So if we know these things, how do we get n by itself on one side? So our sector arc length would be there. We'd multiply by 360, and then we'd divide by the circumference, and this would tell us our angle. In the same way, if we knew the area of our sector, we could multiply by 360 in the numerator and divide by the whole area. Sometimes I'd call that A sub W, W for whole. And we could find our central angle. N would be our central angle. On our foldable, we would call that the measure of arc AB. We could also use N for just a number we're solving for. Cool, so that's 10-1. Let's take a look at 10-2. So it says a tangent to a circle is perpendicular. So if these are told, and they do tell us they're tangent, we can add a 90-degree angle. So notice I have a four-sided shape, and I know all the angles of a four-sided shape have to add up to 360. So one of these angles is 61, one of them is 90, another one is 90, and we just have to solve for this fourth angle we don't know. So notice that's exactly what they did. And so using algebra, when you combine these and then subtract them on both sides, so 90 plus 61 plus 90, you get 241. So 241. So if you subtracted 241 on both sides, that's how they got 119. Also, remember, you could have plugged that in. If you plug that in, you could reconfirm that if this number is 119, then they do all add up to 360. Nice. So whatever boxes, see this word tangent, that means we can add these boxes. We can add these boxes, right? So a lot of this is just Pythagorean theorem and recognizing what a radius is. So we notice here from the center to any edge is our radius. So that's 7. That would make that 7. In order to do Pythagorean theorem, we have to have the length of each side. So we don't know this length. I'll just call that x. We do know this hypotenuse. The hypotenuse is 13, 7 and 6. So we end up getting 7 squared plus x squared equals 13 squared. I get 120, and when I take the square root of 120, I get a fraction, but that's okay, or a decimal. I'm just going to round to 0.95. It's about. And I like this number, right? About 11 looks right. I was looking for a number between 7 and 13. Next one, it says, let's find the measure of CAB. So let's find the measure of that. Let's call that x. We know all three angles have to add up to 180. So we have angle A is x, angle B is 90, angle C is 58. All these have to add up to 180 because of the triangle sum theorem. So this is kind of doing it the algebra way. Most of you have a shortcut for this, but I'll just do it the longer way. If I subtract from 180, I get x is 32. And you could plug this back in to just double check. 32 plus 58 is 90, and 90 plus 90 is 180. All right, 13. Construction argument. If GH is a diameter, so I'm going to just draw a quick circle here, right? If GH is a diameter of T, so we'll call that T, is it possible to draw a tangent to G and H from the same point external to T? Is it possible to draw a tangent line? Okay, so the only tangent line to G is here, and the only tangent line to H is here. So is it possible to draw it at the same point? No. No. So this is number 13. I'm just drawing it off to the side. That's not possible. Because in our lesson in 10.2, we said this tangent line, let's call this another GHIJ. I'll call that J, and let's add a point K. Line GJ is parallel to HK. They don't share any points. No points are shared. Okay. Number 14, we added a box. Okay, so they called this X. We also know this would be X. If the radius is X, we want to know what the radius is, so we called that X. This also would be X. We have a right triangle, right? And we know something about all three sides. So let's put that in our Pythagorean theorem. And this side would be X, right, our radius, plus another 5. So X plus another 5. Okay, so our small side's X, our medium side is 8, and our hypotenuse is X plus 5. So playing this out, 8 times 8. And so this, we should remember, is going to give us 4 things. These two, so this would be 5 times X and 5 times X. So that's going to combine to give me 10X. These front two are going to give me X squared, X times X. The last two are going to give me 5 times 5, or 25. So I end up getting these 4 things, but the 10X combined the two 5X's. Okay, now cleaning this up, let's zoom in a little bit. If I subtract X squared on both sides, it goes away. So this lightens the load here. We have 25 plus 10X. Subtracting 25, and then dividing by 10, and then plugging back in to check for reasonableness. So if that's really 3.9, I was expecting a number less than 8, so I like that. And if this is 3.9, then this would be 8.9, and I was expecting a number greater than 8. Beautiful. So what do I have left? 10.3, 10.4, 10.5. I'm going to cut the video here, check out the next video for the next 3 sections.